Like what? I can't see.
Okay. Well, I will figure out why that is. Thank you. I'll figure that out. Yay, okay. Ready? We talked about all these yesterday. So I think we were on isotonic. We talked about the contractile vacuoles. Do you have these, guys? Say that confidently.
Yeah, we have these notes.
No, do you have a contractile vacuole?
No.
Oh. Yeah, good. Only a freshwater protus. These organisms live in the freshwater. They're constantly taking in that fresh water, and they need them because they have no cell wall, right? So we don't want them to life, so they have them to take ATP, and that's exciting. All right. So what we mentioned yesterday was plant cells and how they cannot pop, right? So I'm going to kind of digress or side note and talk about water potential. This isn't really in this chapter, but you need to know it nonetheless right now. We have an entire chapter on something called transpiration, chapter 438 maybe. We do an AP lab. But if you notice on our equation sheet, the equation for water potential and all that stuff is on here. So that's why we need to know this. We're going to start looking at it now.
Wait, are we ever going to get our grades back for
The math one?
Yeah.
I have them. Most people did really not so. If you want to look at them, sure. I mean, I want to. You just got credit for it in the grade book. I wasn't actually good at it. I want to credit it because Anyways, all right, so let's talk about water potential. So this is what we're talking about now. And I remember this stuff because we come back to this again in chapter 38, which will be happening in like February or something. So we'll have a nice little review of diffusion and osmosis in February again, but I'm going to talk about it now. So I'm going to move around. But okay, so what is water potential? Water potential we only talk about when we discuss plants, things that have a cell wall, okay? And it basically combines the effect of the amount of solutes in something and also something called pressure potential. Why do we add a pressure component because of plants? Why do you think? Yes, which is what?
the pressure that is applied by water on
Against the water.
Yes, yes. The turgor pressure is because of the cell wall. Okay? Remember I talked about yesterday, the water can go in and in, but at some point there's no more room because the cell wall won't expand anymore. Okay, that's the turgor pressure. And so because of that, we have to add this pressure component. So what you need to know, and yesterday I told you to get out this sheet and I never actually talked about it because we didn't get to it. But in the packet of notes I gave you, there's a chart like this. Right in here is what, 5, 6 different ways to say the same thing. All right, down here we have water potential. So get that out, we'll talk about it in a minute. Anyway, you need to know what's in green. Water flows from an area of high water potential to an area of low water potential. What is water potential? Let's talk about it. Water potential is abbreviated as psi. PSI looks like subsidence, sort of. Okay, it's measured in megapascals. And we say that the water potential for pure or distilled water, that means there's no solutes at all, at like regular room temperature and pressure, is 0. Distilled water, room temperature, and like sea level pressure would be 0. So that would be in the picture here, the situation on the left. So there's 2 components to, I'm coming back, there's 2 components. 2 components to water potential. The first one is something called solute potential. Psi-F. Go away. So the solute potential is basically proportional to the amount of dissolved solute. It's also called osmotic potential. The equation for water potential period is water potential equals solute potential plus what we call pressure potential. Okay, so the pressure potential is here. It's the actual physical pressure in the solution. So something that's open, like a beaker that's open to the atmosphere, it doesn't have any extra pressure exerted to that water. Okay, like in this picture here. But notice on the right side, there's a plunger. You see that plunger? That's a physical pressure force. Okay, and that's going to exert a pressure on the solution. So in this U-tube apparatus, imagine that plunger was not there. What direction would this water flow if the membrane was not permeable to the solute? Which direction would the water flow if there's no plunger? What do you think? Say that?
Right.
It would flow to the right, right? And to try to negate, like it would go this way, and the water level would go right. But if you add an external pressure here, preventing any water from moving, that changes the situation where the net water movement would be zero. Anytime you add solutes to a situation, the solute potential is always a negative number, okay? And the pressure potential is usually a positive number. A lot of times the pressure potential would be zero if it's open to the atmosphere. Okay, so let's look at these pictures here. Here's distilled water with no solutes. The beaker's open, there's no external pressure. Solute potential is zero because there's no solute. Pressure potential is zero because there's no plunger. So the water potential would be zero. All right, let's look at a little plant cell that's flaccid. It's a little plant that's like wilting, okay? Plants, because their cells have solutes in them, all cells have solutes, so the solute potential is like -2, let's say. It's not always -2, they just gave a number. But because they're solutes, it has to be negative. Pressure in this case would be zero because it's kind of flaccid and water's moving in. It's the pressure of the wall, okay? So because it's still flaccid and the pressure of the wall, like Turner pressure, is really not much right now, it's zero, we say the water potential is -2. Well, if I take this little dude and put him into this distilled water, which direction will water flow? But just use these numbers to determine it. It will flow in because it goes from your high water potential to low water potential. Does that make sense? And zero is always going to be greater than a negative number. All right. So in this case, a plant cell that is very turgid. Okay. At this point now, we have Turner pressure. Do you see that? The red lines indicate the Turner pressure. So in that case, the pressure potential that the cell wall is exerting is now a positive number. And the point at which no more net water can flow in would be when the pressure potential negates the solute potential. Y'all see that? So in this case, we have a water potential of zero. So in that case, if it's in the distilled water, you know, no more net water will move in or out. Does that make sense? Kind of. We have an entire lab on this stuff way later, but we work on it some next week. So, what's wrong? Yeah.
What did you say about the solute potential being negative?
It's always negative. Anytime solutes are added, it makes the solute potential go to a negative number. It's always negative if there's solutes there. The highest number that solute potential can ever be is zero. You can have a positive solute potential number.
You can have a negative pressure.
You can, yes. And that would be a situation in which you have, let me show a picture with the plunger. You have the plunger here. It's just like a syringe when you pull up. Okay? That wouldn't happen in a plant cell. That's if you would start pulling up here, that would make this pressure potential go negative. And that would make this number go way negative, so it would even go, does that make sense? So that's, yeah. That's actually really lucky. I'm not surprised. I'm just saying. Cynthia all the time about you. Like, because she was like, I don't know.
Oh, she was like something.
She's very impressed this year.
Aw.
I'm trying to tell you about. All right, so here's our cell membrane and here's the cell wall. And it's just the turgor pressure itself is the pressure that's being exerted by the cell membrane on the cell wall, and we have this wall pressure anyway. The point at which those are zero, there's no more net movement of water. Yeah.
Our pressure potential, does it change, like, depending on what you're looking at? So, like, for the plant cell, would it just have to be the turgor pressure?
Mhm.
Okay.
Yeah.
Not, like, the pressure of the
Right.
side. Okay.
Right.
Will we ever have to like find the solute different like that you can give us the solute tension pressure?
Yeah. Now, there's actually, I'll pass these out. This is beyond what we need to know right now, but I'll pass them out so you can see the equations. There's actually a lot more to it. Find the water potential on the back.
Oh, yeah, I remember this was on that question.
All right, so you go to the back. Where it tells you water potential, it's on the right side in that box on the far right. It tells you what those, you taught science, right?
Yeah.
Pressure potential. Now they tell you what these things all stand for, so you don't have to memorize. You just need to know how to use these equations. Anyway, it even tells you the water potential will be equal to the solute potential of a solution in an open container since blah, 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 blah. Look at that. But then they tell you even further, the solute potential equals negative I CRT. Whoa, okay. That is what we're going to work on like next semester in a different lab, okay? So there's ways to determine this stuff, but to answer your question simplistically, yes, they will give you a lot of numbers. It would be the most math you need to know how to do this class, besides like a chi-square and some random statistics type thing, is algebra 1. Okay, so you just be solving for a variable. Yeah, everyone in here should be fine solving for x. Okay? So, anyway, all right. I want you to look at this for a second. Let's look at this. We talked about water moves from low to high. Now I talked about water moves from high water potential to low water potential. There's a lot of different ways to say the same thing. So that's what this chart's supposed to help you with. So look, it says water moves across the selectively permeable membrane from high water potential to low water potential, high water concentration to low water concentration, low solute concentration to high solute concentration. You see how it's the same thing, just different ways to describe it. Hypotonic to hypertonic, low osmotic potential. And what did I say osmotic potential was? It's the solute potential. That means not a lot of solute. The high solute osmotic potential, low osmotic pressure to high osmotic pressure. All right, so same way to say the same thing. This is different ways to say the same thing. Just to kind of help you keep that all organized. And like I said, the rest of these are just extra notes. Yeah.
So is it that like low economic like high water potential? So
Yes. Yes. Yeah. Exactly.
like high water potential.
All right, now I'm moving back to the other PowerPoint. Good. All right, let's talk about our flat or our shrinking cells. Okay, I think I talked about this yesterday, right? So a plant cell, well, stop. An animal cell in an isotonic solution is healthy and happy. What is my question? It's healthy and happy. No net movement of water. What? No, Tyler just got me a new one. I was using it.
Is it over where you grab the stuff from?
Oh, it's right here. But I do. Wait, no. Isotonic. That's what I'm talking about. Isotonic. Animal cells in an isotonic solution are healthy. Okay, so this would be like you going to the hospital and getting an IV solution that has some salt in it. They would never give you distilled water, and they would never give you salt water. Both ways would kill you. They would do that. I do, I know.
Science says it.
I know, they
I
would.
can like give
There's a lot of ways to kill ourselves.
But you wouldn't do that, and I wouldn't do it too.
1,000 ways to die. We should start recording every time he says that, and it should be like,
Because some things, if you taken out of context, it'd be really bad.
We gotta do like a project, like take a really interesting way to die, and explain like biology.
You know, that would actually be kind of cool.
Right? So
Like
like,
cyanide poisoning, we can talk about that. We can talk about the electron transport chain.
yeah, and then you can find out what happens if I die. I would really die.
End of the year project after you guys.
Because like getting
Yeah. I'd be very
Okay, it's like, it's just like that impact that everything I'll push forward, get something and something.
Like, don't give me that. You would think. Alright, yeah, we need to move on because we need to work on these sinus problems. So anyways, alright, so isotonic solution is healthy for animal cells. Plant cells, however, they're not dead, but they're not happy. So plant cells are what we say flaccid, okay? Say flaccid, everybody say flaccid.
Flaccid.
So you say that. Okay, so this would be when your plant is starting to wilt, okay? It's flaccid, it's becoming flaccid, you need to water it. They're not dead, they're just not as healthy as they could be.
Wait, Ms. Wagner?
Yeah.
Does it also get plasmolized?
No, that would be,
That's just with hypersonic?
Yeah.
So then, what kind of solution does a plant cell want to do?
Hypo. Doesn't want to be in, doesn't want, but healthy, yeah.
It has
So-
a purpose.
To go back to what we talked about yesterday, a hypertonic solution. This would be like watering your plants with salt water, or giving you a saltwater IV. Bad idea. Okay, super salty IV. All right. Animal cells will shrink up. It's called crenate. They could die. All right. Plant cells will undergo plasmolysis, where they'll keep losing and losing and losing water until the cell membrane pulls away from the cell wall, like they're showing in that picture, and that will cause death in a plant. So, none of these things are healthy. So, aquaporins, you read the article on that and answered the question. In biology, sometimes when you ask questions and I'm like, well, most of the time or what we know or so far or whatever, or you say something, I'm like, well, I won't say never. Because when I took Bio 1, my biology teacher, even my AP bio teacher, taught us that water moves directly through the membrane, through the lipid bilayer. That's what I learned. That's what I learned. It moves through the bilayer by itself. It was small enough that it could do that. That's what I was taught. But when I was in college, okay, these people did a lot of research because they were like, I don't understand. Because water is so polar. How can it move through so quickly in a place like your kidney? And it does. How can it move so quickly through certain cells of your body? It doesn't make any sense because it's so polar. So they did a lot of research and they actually found that it doesn't move through the membrane. If it did, it would take too long and we would actually die. There are protein channels called aquaporins that, when they're open, allow large volumes of water to move via osmosis, and that's how it actually happens. Very rarely will water move directly through the bilayer by itself, if it does ever. It's too polar. It's too polar. So these guys discovered it, and this paper was published when I was that's 2003 is when I graduated graduate school. So, I actually didn't learn about this till I was in, I started teaching. So things can change. So what you learn now can totally change in even 5 years. It is, I know.
You think about you can be taught something and then 5 years later, it's all these.
Yeah.
You were lied to your entire life.
So anyways, so that's that. And I hope the article was interesting. The article was relatively old that you read, but, okay. All right, I want you to do this, like get out a sheet of paper. We're gonna work on our first problem, then we're gonna work a bunch of problems. No, this one we're doing, you can do this on scratch paper. Yeah, take the red paper. So this is a hypothetical situation. That bag is like a dialysis bag. Okay? Now you have to know a couple things. First, when I do problems like this, I always draw it. If I was given that, like first of all, if this was given to me like on a test, it was already drawn for me, that'd be great. But I'd be drawing arrows on it. If I was given it on the board, I would draw it on my paper. It would make more sense to me. That's what I would do, I'm just saying. So if I tell you that the bag is permeable to glucose, it is not permeable to sucrose. Those are very important pieces of information. It is permeable to glucose, it is not permeable to sucrose. What is sucrose, like mono or disaccharide?
Fructose? No, monosaccharide.
It is permeable to fructose as well. It's permeable to mono but not disaccharide. Too big, okay? This is like a dialysis tubing. Like when we do our lab next week, did y'all use dialysis bags and buy one?
No.
Raise your hand if you don't know what I'm talking about. Okay, that's okay. What? Well, you're talking problem. I'm sure you did. Did you not?
I didn't really buy one.
We might have.
Well, next week will be our fun, very colorful lab, and you get to work with dialysis tubing. Okay. Anyway, so permeable to glucose and fructose, not permeable to sucrose. So I'm going to help you along with this. The first thing that you need to do when you're faced with a problem like this is you need to take care of everything that will diffuse. Diffuse all the solutes first before you worry about the water. So what's going to happen to the fructose?
Wait, just find out which values are in the environment and which are.
The cell is the bag. These are in the cell.
Okay.
The environment is this stuff. Oh, okay. So what's going to happen to the fructose?
0.05%.
So since there's no fructose in the cell, honey, what's it going to do? It's going to diffuse into the cell until what? You gave me a number.
0.005.
It'll diffuse in until it reaches its own equilibrium. Okay, which is outside and then inside, right? Does that make sense to everybody? All right, next, let's take care of the glucose. It's 0.01 outside the cell, 0.02 inside the cell. Which one is the higher concentration, Nicole? The 0.02 or 0.01? So which way will the glucose diffuse? Outside of the cell until it reaches what? Which is
0.1.
0.
That would be a lot.
Okay, good. So that was actually diffuse in. Now, we've taken care of all the sites that will diffuse. Then what you do is you then add up the solute concentrations on either side. So add all these up and add all these up and come up with a number.
Wait, what about sucrose?
That won't diffuse. So we're gonna, hold on.
I missed that. Right?
Oh, yeah.
Sucrose does not diffuse. So the first thing you do when you do problems like this is take care of all the ones that will diffuse by themselves. So we just did that. And then what you do is add up all the solutes inside and outside the cell. Tell me what those numbers are. What are they?
0.02.
This one?
Including the sucrose?
All of them.
0.03. All of them. 0. Oh.
And then the inside is 0.05.
All right, so inside of the cell or outside the cell, which one has greater total solute concentration?
Inside the cell.
Inside the cell. So now we worry about the water. Water moves from an area of high water potential, low water potential, high water concentration, low water concentration, la 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 la. Which way will the water move?
Yeah.
Into the cell. Okay, so they answered the questions at the bottom. We just said we'll go in. Okay, so after we took of everything, compared to the beaker, the cell was what? Hypertonic, because it goes third to first. And then the beaker would be, was that all pretty easy? This is kind of the basis. Did y'all work on that packet at all last night or the night before? This is the stuff that you were doing, right?
Yeah, but it was simple.
Well, get ready for this. All right. So now what I want you to do is you're going to, well, we need to go.
So why won't the
It's a disaccharide and it's a really big molecule. In the lab we're doing, you'll have to figure it out on your own.
So, then in the science of guys, how big is the water?
They're tiny, like, but you would have to know, like, when you buy it or something. They're certain size. All right, y'all look at,
Only allowing a molecule of.
Yes.
yeah. Look, you are going to have to get with people around you. You can move your desk, but I don't want you to get up and move. So work with a few people around you, and what you're going to do is you're given this situation. They tell you at the top, it says the following questions refer to the diagram, blah, blah. There's a selectively permeable membrane separating the two sides of this U-tube apparatus. It says the membrane is permeable to water and to sodium and chloride ions, but not to glucose. It's set to stand for 3 days. On the back are different statements. So what you have to do for each one of these is basically give it an A, B, C, or D. So for each of these questions, the ones on the back, select the most appropriate phrase. So either both the statement and the reason are correct. The statement is correct, but the reason is wrong. The statement is wrong, but the reason is a fact or a principle, or both the statement and the reason are incorrect. This is going to take you a little bit. Again, remember, before you do anything on the back, you need to do the front. Figure out what diffuses what, which way, again, the water will move, figure out which side of the U-tube apparatus will shrink, which side will rise, and then start doing these. Once you think you have all these, come check in with me. If you have a question, let me know. I'm going to be walking around.
I started writing pen before I wrote the question. Thank you.
Okay, work with people around you. You probably shouldn't do this by yourself. Did you register? Did you like sign up for one? Oh, okay. Oh, great. Look at you. Your mom. All right. Do you bring out high school? Yes.
Yeah, you guys.
Okay, so right here for today's day, the 10, 12, and then 20 $20 for 0. You're right. Actually, write the word.
Yeah. I think you're thinking, I was
And then, not necessarily. So you need to figure out what and then add up this little
soil concentration to find and see what's at the market.
Thank you. Have a great day. That's okay, thank you.
You get CAAD.
Now figure out what happens first. Just use the ion, then figure out the water, then you water.
Yeah, okay, I thought high street and then yeah, I got
Because of the water.
Well, they're gonna equal each other out. But they're gonna equal each other out. Oh, wait. Yeah, it's gonna equal each other So you know, everyone has to be short. The longer I feel bad, this is fine. So I like the
What's that?
You said you had
Oh, yeah. I can't find my candy. So, hold on.
Why would we hold that?
Yeah. Work on tracing this right now. Work on tracing this right now.
What's wrong?
Because the substance. It's not. It Okay, blue level will rise.
But it's not like they have more free.
No.
They have a side.
Pretty water.
Yeah, substance.
The reason it's correct is water. I think it's
Lower to higher. Well, look, the water's not gonna eat you from that wire. It's
You're thinking about what?
gonna eat you from that wire. Yeah. So then it's not gonna be.
Yeah.
Oh, the boat.
Number 2 is not right.
But it was kind of lower. Kind of low.
Alright, you have the right answer.
Kind of low.
You're at B.
Oh, I don't
They'll still move, but the net movement actually does stop. We say the net movement is like the bulk movement.
Okay.
So they still move, but the net movement comes here. Fighting.
Yeah, okay, I second guessed myself.
Number 2 is not A.
Number 2 is
That's all right.
Yeah.
How do you think?
What's the mean by concentration? Like,
Number 2 is not A. Copy, but. Wait, why?
Oh, it is impermeable to glucose.
Yeah. Oh, I just made this.
But it will be free sometimes.
Yeah.
Same kind of thing like. So,
I said A, no, I said B for that too. Somebody else said
I said it was D.
hold on, I'm figuring out. I lost my key.
I put A for
School level inside water, will be free, yeah.
It doesn't only. That's why it's wrong.
I was just saying that statement was right. School level inside exercise, water.
Yes, number 10 is B. Number 10 is B. I mean, what is B? I just looking at the wrong one. I just looking at the wrong one.
Because the one also is that not necessarily, but it has like the net is different. Got it.
yes.
I don't think. I don't. Why would
Oh, wait, no, number 1 is B? Yeah, because like,
Okay,
will become more concentrated. So side X,
so fluid on side X will rise. It
it's
will
gonna go
rise.
from point
It
1
says
to point
because the
1.
solution on side X had a lower.
Right, side Y is gonna become less concentrated. So it depends to diffuse.
I'm so low central, right?
Oh.
Wait,
Wait, so it's gonna be side.
I thought
I thought water molecules
The reason is
from roots of high
it goes from low
We're talking about size. Yeah, okay. So water moves from low osmotic potential to high osmotic
It
potential.
goes from high to low.
So it's moving from side Y to side X.
So it is
Side X.
That's higher.
Side
Those are
Y. They're higher, right?
Side X have higher lower.
Right.
wait. It goes from low osmotic to high because the high goes from 22 and it goes to the low side. It was 0.015. And you just take the light and you all the way down. Everything gets. I don't know why I did that.
That's the root, right? Water molecule is Y to side X. Water will move from the lower osmotic potential.
Why is number 9 side? Because the food on side X is in the red.
I mean, maybe you were like.
Oh, yeah, because we did a lot. Wait, that's why you're 2A or not?
It's not A.
2C.
Oh, coffee.
Last one is A. I just wasted half of the See, originally I thought number 4 was a different one.
Look, the concentrations of glucose on side X will decrease, and it does. Right? It does. It decreases because water moves. So when water moves over there, it's going to dilute the glucose concentration.
So it's gonna become more
Yeah. Well,
Yeah, I think I was this too.
and then look, water on side X will rise.
Yeah.
It does rise. Because the solution on side X. So water moves from low osmotic potential to high osmotic potential, right? So it moves from Y to X to low osmotic.
The reason for like
Because the solution on side X has low osmotic.
Oh, okay.
Hi,
How's it going?
good. You live out in the Outer Banks up here.
No, I do.
Wait, but that's B. But the statement is correct and the reason is incorrect is B.
What?
The statement is correct, you said the statement is correct, but the reasoning is incorrect for number 9. So it should be B.
Yeah, why did I put I put the wrong one. I'm sorry.
Yes, it's right. 8 or 9 is actually.
That's right. Here, number 4.
Oh, okay, here's what I want to do.
Yes.
Can I look at the shirts before, because I think I'm gonna get my daughter one instead of myself too.
Okay.
But I might end up getting 2 short sleeves and just giving you the extra $5 since I've been such a pain in the butt.
Oh, that's fine. Whatever you want. They're back
I'll
there.
put this in the bank until Friday.
Don't worry.
They're back there, but do I have to take
Here, hold on. I'll help you. Wait. Actually,
Rebecca, come over here. Why is it because, okay, more water. I like Starbucks. Yeah. No, we really have pressure going to skip right. And then we all got to go like. And Mr. Fry was. Yeah. So he was like, okay, everyone at 102, we're all going to talk.
No, are you gonna ask her that question?
No, it was one of the circles went off. You remember that? Were you there? Her phone went off, and she got mad, and she was like looking around. Wait, was that in Pablo? Yeah, yeah. So she was looking around like, who is this person? Who is this idiot? Yeah, it wasn't on. You know how she had that like glass clock like perched on the thing, and it like fell. She was ready, it fell and it shattered. Her phone went off. Now, what is this? That is like Lord Death. I have
Yeah, I know. You don't have to text me. I didn't even hear if that was.
Well, you don't make them. Evidently, definitely they have to just a little bit out. They had me surgery yesterday.
I'm done. What are you doing? I'll blame her like this.
Like, where you're not supposed to do it. And where it's
Yeah, I know. I finished you were still writing, and then I turned around and was like, yeah, thank you. And then bring it back to you.
Right, y'all, we're gonna talk about these. Does everybody have a chance to do it all? No. I had some dudes in the library the other day, all and like, yeah. That's what you're saying. It's like a tough ball. Yeah, I guess it's like you said,
My family's from Pennsylvania, passing like
Oh, I love it. The bookkeeper of all the people that like have to turn in checks with phone numbers on it. She didn't put her phone number on her check. All right, y'all, let's talk about this. And then I will give you the rest of the slides that was on your packet. Orange field,
We have and the bride is Kyle, and she's like 6'2" with her entire outfit, so she has one. And the wedding picture, all the wedding. Yes.
like today.
Oh, yeah.
I'm
breaking them in today.
Lesson number one. The sodium, okay, so this is what happened. So let's look at it. Number one, the sodium chloride solution on side X will become more concentrated, and that on side Y less concentrated. Is that true?
Yes.
Yes, okay. because a substance tends to diffuse from regions of low concentration to regions of high. Is that true?
No.
No. So what would that one be? B. All right. Everybody understand? Please ask if you are confused. All right. The concentrations of the glucose solutions on side X and Y will remain unchanged. That is false. Tell me why that is false. Jacob?
Because when the water does osmosis to the other side, it increases the amount of sulfur, which decreases the amount of solute, and that decreases concentration.
Yes. Because water is going to move from side Y to side X, it's going to actually change these molarities. The definition of molarity is like moles per liter of water. What you're doing over here, you're not changing the amount of like moles of the glucose. What you're changing is the amount of water. Because the water is leaving from over here and it's going over here. So this concentration is actually going to do what? Decrease, and this one will increase. Okay, good. So the first part is wrong. Because the membrane is impermeable to glucose, and so glucose cannot diffuse from one side to another. So what is that? So what's number 2? C. All right, number 3, the concentration of sodium chloride on side X will eventually equal that on side Y. True or false? True. Because sodium chloride ions will move by diffusion from one side to the other, gradually reaching uniform density, and then that movement of ions will stop. That's basically true. The net movement will stop. Now they still will move, but the net movement becomes 0. So 3 is okay. The concentration of glucose on side X will eventually equal that on side Y. True or false? Now we're on number 4. Where are you?
Yes, true.
True. Because water molecules diffuse to the membrane from side Y to side X via osmosis, thus lowering the glucose concentrations. What is 4?
A.
4 is A. The fluid level will increase on side Y and decrease on side X. Is that true? No. And then because water molecules will move through the membrane from regions of high to low concentration of water molecules. So what is 5? 5 is C. That second part is actually true. The fluid level on side X will rise. True or false? Come on, y'all all done this, right? True, because the water molecules on that side at the beginning of the experiment have more free energy than those on side Y. That's false. They have less. There's more free water on side Y, so there we go. So C is what? 6 is what? Sorry. The net movement of water will be from side X to side Y. That's what? False. Because water molecules will move from the solution with the lower osmotic potential to the solution with the higher osmotic potential, blah, 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 blah. What is that?
C.
Okay, so remember our little chart? Same way to say a bunch of different things? Or different ways to say the same thing? Water moves from low osmotic potential to high osmotic potential. So what is number 7? Speed. Yeah? About what?
Number 1.
Number 1?
Yeah, just like, because on the sheet it says that water moves from a low solute concentration to a, never mind. Never mind.
Okay.
Tyler.
Are you good?
Yeah, I'm good. I think I just read it wrong.
Okay. Number 8, water molecules will move from only side Y to side X and not from side X to side Y. Is that true?
No.
That's false, because water molecules move only from regions of high to regions of low concentration.
They tend to, but they don't own.
Right. So I would say 8 is D. Fluid on side X will rise. Is that true?
Yes.
Yes. Because the solution on side X had a lower osmotic potential than side Y. False. False. So what is number 9? Okay. Number 10, water molecules will tend to move from side Y to side X. That is true because the net movement of water molecules will be from the solution with a lower osmotic potential to the higher osmotic. Concentration potential, same thing. So what is number 10? Yay. Yay. Did this help? You understand kind of how to do this stuff and what those things mean? This was done, this is like an actual college biology like thing. So give yourself a pat on the back. This is a college biology course, so you should know you're doing college work. Okay. So when I was in high school, we didn't have AP psychology, but we had psychology 101, which was through USC. So when I was a senior in high school, I was actually a legit USC student, like I went and got USC for USC and all. It was actually pretty awesome. What?
They do that.
Oh yeah.
Yeah, they're doing like.
Yeah,
Yeah.
I don't have.
I wish.
Okay, you have the rest of the class to work on this. Or to work on your reading guide, the student mind. Put those back in there, pretty please. Y'all, your equation sheets, please put them back in the folder over there. You can. Yeah. Yes, you can. Yeah.